Hello, viewers, and welcome to another learning episode. And today we're going to look at just a brief revision. It's an overview of a lecture series that you have just completed, Introduction to Finite Element Methods. And of course, you can always watch the recorded videos, lesson 1 up to 7, that we have kept in this playlist up there or in the description box there. And today we want to see a typical exam question, and we do this by looking at an exam that was done last year by a graduate student, Bachelor's of Science in Civil Engineering, and that is in 2020. And we are going to see typical questions that are usually set. These are university level questions. There are two sections usually. We have one is question 1, which is compulsory, and of course there is the optional questions. In compulsory question, this unit is called Theory of Structures, and I take the word theory in terms of understanding the basics behind the structural analysis, like finite element methods. So you may find like I'm focusing on the theory on the part 1, but I tend to put short structured questions. I try to give short calculations, and also I want to test on the theory. Because basically, many structural analysis exams, you just find that you are given like a truss analyze, you're given a beam analyze, but do you know the concept, the philosophies behind the analysis that you are following, the procedures? So sometimes you may be asked some brief questions there, and that's what I do in question 1. This is my style, and this is a standard university style from where I teach from. And I think you can appreciate that because it helps you to not only be so mechanical, so robotic, just going to analyze a structure, but we need to understand the concepts behind. So let's see, and I'll do this by sharing. Let me share my screen, and then I think I'll open one typical last year's question is our reference and question paper. So this is typical we are saying this is a typical exam. I know after a course series you get the exams, and I want to demystify that fear of tackling the exam. So this exam have been set and moderated by external examiners and professors from different universities. So it's a standard exam, which was done last year. Usually covers 2 hours. And this is what I'm saying. I may have removed the instructions. Usually we have the instruction part here to begin with. I don't know whether I can get, let me look at just another question paper. Let's see this supplementary question. So I wanted you to see, we always have the instruction part, like you're told it's a cross-book question, so you may not refer to any book, you may not refer to any written materials. Anything that is necessary, required for this exam, you might be given. Like in this case, the stiffness matrix for a plane frame can be expressed. The word is can be. Of course, you can express it in some other form, so as given here. So an answer booklet is provided. A scientific and program calculator is allowed. So this is what I wanted you to see. Question 1, I usually put it compulsory, then you just select any other 2 questions. This was a supplementary question. Of course, there is a fast take, and then if there is a problem and there's somebody who didn't pass or somebody missed the exam, usually after approval by the university, we have the separate exam. So that's why I'm saying supplementary. So my focus is not on that. But if you can look at this, and this is what I'm saying. Question 1, I usually put kind of theoretical, short questions, short derivations, short calculations. You see, short derivation, calculation, and so on and so forth. So that by the time you are coming to question 2, 3, 4, 5, you choose any 2. And this way you just have to do the calculation without having any theoretical write-up. Sometimes you may wonder, okay, maybe this is not the style that you have covered the theory of structures 1 to 4. But I find this helps the student to understand the overall concept, because some of these things are not the things that are in the notes, but what we talk in class. All right, let's go to the question I'm interested in the main exam, which was done last year. And then we are looking at the part 1, which is compulsory, 20 marks. Short question, like you can see here, you ask a question, and 2 marks. Another one, short one, 2 marks. You're given a spring system, 2 marks, 2 marks, 1 mark. So it means you should not spend time. You should not write histories. There are groups of students who are telling me that the paper was long, but when I went to mark, then I realized that they are writing stories. No, I am not calling for stories here. You need to write short, brief questions, brief statements, and so on and so forth. So on and so forth. Derivation, short derivation, marks distribution are shown here, another derivation here. So total, 30 marks. These are like 3 marks. And you should be able to handle these within 45 minutes. Yeah, because the total exam is 2 hours. So 45, if you do 45, then the other one you can do 30 minutes, 30 minutes, 30 minutes. Or even 35, you still have time to repeat. So today I want us to look at the part 1. So part 2, basically we have looked at this kind of examples, just analysis of a truss, this is analysis of a beam, this is analysis for a frame. And in fact, I gave 4 questions only. You choose you do question 1 and then 2. Then here we have some useful expression, like the expression for the general expression for a frame oriented in any direction. For a bar and for a beam. But these are just expression. You can use the one that you remember. In case you need the reference, you can use this one. Right. So let's see what are the typical example, or how can you go about answering this? Let's see the model answer. And I believe this one I gave is as a tutorial. So these questions, you can also download them. If you go to the link in the YouTube link section, in the description section, you get the link to download the question paper and also these model answers. So now look at this. The question was, in the recent past, the finite element method has become a popular tool for analyzing structures. Justify the statement. So the requirement is, why is finite element method popular? We said in lesson number 1 that this method became popular from 1960s when the computers became available, because we found that there are so many equations that need to be solved. So the reason why it's popular, one can model irregular geometry, because maybe the analytical method that you have been using, the Macaulay's method and all that, maybe then we have challenges in handling general conditions, complex boundary conditions, unlimited kind of boundary condition. So in this case, like here, so you need to, this is how maybe typically I might be checking this. So you see, because there are so many and this is a short one, so you can say model regular bodies. So for each one of these, I can give you either half mark for each one of it. So if you give me any 4, I multiply by half, so you get your 2 marks. And they don't have to be lengthy the way I have stated here. Like you just say model irregular boundary, handle general condition, model different materials. So short answers, and that's done. Then the second question was using a flowchart. You are required to illustrate the basic concept of finite element method of structural analysis. So if you look at this, you are to use a flowchart. This is just a typical example. This is basic. This is a flowchart. So we want to illustrate the concept of finite element. So we wanted to see you describing from a complex object how you move to simplify the analysis, because now you know the finite element method of analysis is basically a simple algebraic equation, simultaneous equation. So how do we do this? By discretizing. So either way, you can follow the above, the top one, the top approach, or you can maybe explain briefly, like from the real world, you simplify the physical model, then we have the mathematical model, we discretize the mesh. So in this, that's why you're saying you can have one here and then another one here. Somehow, if you incorporate some terminology from here, and then you mentioned about the modeling part in here. So mathematical model, you don't have to write both of them. Okay. So that's that. Let's see the other part. So they are short questions. Now you are given a figure, a spring system. You found that in the question paper, and you are supposed to answer a number of questions here. So this is the spring system that you was given, figure 1-1. So it has got a series of 2 springs, and then you are required, number 1, use the direct stiffness method and employing. Now this is where you might be caught, because the question clearly states that you need to employ the force equilibrium criterion. So I don't know whether you still remember. We have the force criterion in coming up with the finite element method. I think this is lesson 2. we were able to start with the force equilibrium method, and then we went to the issue of compatibility, where we superimposed. We just need to realize the common nodes, and then we superimpose the equation. But here you are categorically, you are clearly expected to use the force equilibrium method. So this is one check. If you use a wrong method, like the compatibility, the superposition principle, then you might lose it out. So, and of course, after the stiffness matrix that you're going to get, you are supposed to show that it's symmetrical and singular, and comment what this means, what this singularity means. And finally, for the spring element, comment how suitable they are as finite element tools. So let's see how you could have gone around this. So first, we said force equilibrium equation. So you have to use the issue of equilibrium, force equilibrium, right? So that now you can write. So today I said it's an overview. So we are not calculating, because actually it's in the note directly the way it is. So I'm just telling you or showing you how you should have come or how you have approached this problem. So you write the force equilibrium for the first spring, for the force 1 at node 1, force 2 at node 2, and force 3 at node 3. Refer to that lesson 2. But what I wanted to elaborate is that you have to use this force equilibrium method. So I don't want to see you writing K minus K, and also K1, K1, minus K1, K1. And then you start superimposing, because you'll have lost some marks because you did not follow the correct method, right? So number 2, so that's you are able to obtain the global finite element equation. And from here, you are required to explain, to show that, of course, from here, we know that this is a stiffness matrix. So the global stiffness matrix, so we just extract. So K is extract. We have F is equals to K, and of course, displacement component, delta, deformation vector. So K is this part. So now we are, by inspection, you are supposed to show symmetry. So symmetry is that this is the main diagonal. So you show us that these and these are the same, or whatever is on this side can be mirrored across the main diagonal. Okay. So a singular matrix, again, you are to show or to explain, I believe the question was, show that the stiffness is symmetrical and singular. Singular matrix have got no determinant. So what you are required is 0. So what you are required to obtain is the determinant. So you can use the Cramer's rule, you get the determinant, which is 0. And from there, since the determinant is 0, so you have to comment. So it means K is not invertible. We cannot get its inverse. And therefore, there is no unique solution. And U cannot be found. And if you remember carefully, because of that singularity, then that's why we needed to employ the boundary conditions, so that we can be able to determine the U. So there's somebody who was asking a question, can we apply the boundary condition for an element before we come to the assembly stage? So if you look at this system of, although this is a spring system, but there are no boundary conditions. So it's like the spring system is floating. It's like we have extracted part of the element from a bigger structure, which was supported somewhere, because it have to be fixed to one head and load applied. Otherwise, it will be floating on space, what we call the rigid body motion. Okay, there will be no deformation. So that's why we are saying we need to apply boundary condition. If our system is made of one element, like if this was just one element and then there is a boundary condition is fixed here. So if it's fixed on this end and we pull on this other end and it's just one element, it means now the local stiffness matrix is the same as the global stiffness matrix. And in that case, then you go ahead and apply the boundary condition. But if it's a big structure that you have discretized, the element you have extracted doesn't have boundary condition at that point because it was connected to another node. That's why we have to do the assembly. Okay. So finally, commenting on the suitability, of course, we say they are not suitable for stiffness analysis. This was in lesson 2. And because the load is actually not applied on the cross-section. Remember, it's a spring, so if force of an area. So the load is not applied on the cross-section of the spring, the wire themselves, the wire itself. You can use that term in code. And of course, we can have spring in any direction lateral. We can have spring for torsion and so on and so forth. So they are suitable, they are good, but 3. Because you're saying They can help us in different direction for torsion. The state spring are useful, for example, when you're analyzing sinking support. But again, there is an advantage and disadvantage. That's the word suitability. How suitable? Suitable doesn't mean it's good. It can be unsuitable, but the suitability tells us the good and the bad. Then I gave another interesting question here, which we are saying, using clear sketches, illustrate the possible degrees of freedom for the following types of structures. And this was just to test your understanding. Like when we said for a bar element, 1D element have got only 1 degree of freedom per node. If it's let's say it's along it's the local coordinate system. We are not considering the global coordinate system. So we wanted to see, do you know what is the degree of freedom and how we talked about with reference to the Cartesian plane. So when we said for a beam, we have both the displacement, vertical displacement, and rotation. Can you visualize them or represent them in a sketch? Because for engineers, we have one common language across the globe. And I don't understand Chinese, Japanese I know a little bit, intermediary. Maybe, of course, it's evaporating with time. But even if I pick a drawing made in China, I should be able to understand some basic, because drawing is our common language. So wanted to see your understanding which you have in your mind. Can you be able to put it down, express it in a sketch? So like this for a beam, we say there are 2 degrees of freedom. And now this one, you could do it in 2D plane. This one I choose to do in 3D. Not in the of course, in 3D, Cartesian plane, XYZ direction, so that we can be able to see for the beam, when we talk of rotation about the z-axis, we are seeing the z-axis, so we talk of the rotation, so moment will occur. And then when you talk of vertical displacement per node, so I'm showing v in the y direction. So for the beam, there is no axiom. So on the x-axis, there is no degree of freedom. So this is a beam floating on space, then I'm showing you the degree of freedom. So for the space frame, here you could or you could not show, you may or you may not show a typical frame, maybe just an inclined bar, which is a combination bar, and then you introduce the beam degrees of freedom. So in this case, I just chose to show the degree of freedom per axis. So in this case, moment, rotation, and displacement will be experienced in either of the axes. So that's typical. You can do it in another way. And you see there are 4 marks. So each one of them 2 marks, 2 marks. Good sketch, good notation. Good sketch, good notation. It doesn't have to be exactly like this, but at least we are testing the understanding of, do you know what are the degrees of freedom? When you say there are 3 degrees of freedom or 2 degrees of freedom for the beam per node, do you understand that? Can you visualize? That's a test. That's a check. Now, good. Finally, I wanted this to be very quick because actually we are not solving anything. We are just moving quickly. So it's saying, the displacement in the positive x-axis for a 2-bar node element can be expressed as shown here, where n1 and n2 are shape functions. We talked about shape functions, I think, in lesson 1, as 2. Elaborate the significance. Now you see, apart from just deriving, can you explain why do we need shape functions, right? So, shape function, we said they are interpolating functions. Right? Why do we need to interpolate? We always interpolate. Like sometimes you may have data, like at day 1 you have data, at day 2 you have data, but you want to see result at day 1.2, right? You don't have that data. So you got the approach, the method to determine at each of the exact, and this is what we are saying, the node. Day 1 is node, day 2 is node, but 1.5 there is no node intermediary. So if it was a straight line, we can use equation, linear equation, y is equals to mx plus c. But sometimes we might not be able to get a closed form solution. We do not have an exact solution. So we need to interpolate. And therefore, we have an assumption. We generate using an interpolating function. And remember, this interpolating function, they are polynomials. And the order of the polynomial will depend with the anticipated shape or distribution. So that's why we say we assume a solution shape or distribution. And for the bar, because we say that it behaves like a spring, so within Hooke's law, so we expected to have a linear deformation. That's why we had a shape function. And this shape function, in this case, it was just a straight line like that, increasing. That is, at the start is 0, and then at this end is maximum 1. And then we had another one when we are at node 2, going like that. So what we are saying is, for the bar, the linear. For the beam, remember, we said for the beam, we could anticipate this kind of deformation, right? And we went about and talked of having quadratic, cubic kind of an expression for the beam element. And the polynomial order, of course, was order 3, the polynomial to the third degree. So why we need the significance of expressing as a mathematical function is because it's not always possible to have closed form or exact solution. That's why we need to interpret. So then, if that's the case, why need to express? Then what are the shape functions? And then you start from basic principles, derive the shape functions. So shape function, of course, these are just interpreting functions. This is kind of a repetition of the part 1, this one here. Once you know this, then basically you are going to understand this. So the first one was to guide you so that you can answer the second one. So these are interpreting functions that assume the displacement field. They assume that within that from this node to this node, this is how the displacement will vary, whether linearly, if it's a bar, whether in a quadratic manner, in a cubic manner, like so on and so forth. And then we can use that interpreting function to be able to get. And I think I need to make a good video on, not a good, but a slightly detailed video on shape function, because you may realize that as you advance, right now you have started talking of software as finite element analysis software like Abacus, you'll have to consider a case, sometimes convergence or getting exact solution. You may need to use a higher node element. That's why we introduce the middle node and we start talking of the interpolating function now, coming from linear now to quadratic, but within that single element, right? So maybe later on, or watch out for that. I might prepare that in the future, in the near future. Okay, so we have finished the theory part. So now deriving this one, you can refer to lesson number 2, how we moved from, we had a prismatic bar, linear elastic, and then we assumed, so this is the first place you assume a linear relationship, the displacement at any one point will fall in a linear manner, and then you to obtain this constant. So I don't want to go through this because of course it's covered in that lesson too. Right. But I was showing you how you need to move with speed, because this is 4 marks, so you don't expect much. So the first part maybe this is a half mark, then this one will carry 3.5 marks, obtaining that and up to the end here. And then this is a sketch for shape function 1, shape function 2. Again, you are given the bar element, which has a cross-sectional area and elastic modulus of A units and D units. Show that the stress in the element can be expressed as shown here. Here you are being tested about the issue of strain displacement matrix, and where you can, you know the second step, where you are defining the second step of finite element analysis procedures. We talked about 8 steps. This was in lesson 1, and in that, there's a step we said you have to define the stress-strain relationship, right? And the material relationship, stress-strain, and of course, strain displacement relationship. So this is where, because already you have derived this expression in the first part, part 2, so we wanted to see whether you can remember this expression. Strain is changing the derivative of the displacement, so that once you derive that, you get the derivative of that, and you express in matrix form. Now you introduce what we call the strain displacement matrix B. So it's very simple. Again, I'm saying you can simplify these steps, but at least you should do it in a way that nobody will think that you copied it. Yeah. So here, because I'm giving you this outline, I might have put so much of the information, but for your case, but I don't think what you can jump here. You need to see these steps, and you can see how I'm outlining them very carefully. Sometimes when I'm marking, like I was marking the CAT, the continuous assessment test, and then somebody is writing here, is writing on top, is writing with the pencil here, is cancelling. So getting to get that through becomes very difficult. And you see, like now in this semester, we are having a class of 170. So we don't spend too much time on one paper. So if your work is not flowing well, then you might end up losing some marks. It's always good to ensure flow of your work. Good. Let's move to the other one. This one is a quick one, is an overview. For a linear elastic beam having its length as L units, loaded by shear forces and bending moments only, the transverse displacement function B can be expressed using a third order polynomial. Now here I've already given you the order of the polynomial. So a beam, I hope you can have it. Yeah, this is one that's in your notes. This is lesson, I think, 2, 3, 4 on beams, right? So all this is in the description. You just need to go below this video. And by there, as you pass by the video, you need to click the subscribe if you're not. Then below there, you click, there's a description below there. Sometimes it just shows the first 3 lines. You can click show more. You're able to get all these links there. So for all the lessons. So because of this cubic expression and how we say our beam, because as we apply positive node of forces and moment, we expected or we anticipate to bend like this. And this now, the shape function, or we assume the deformation nature could be cubic. And that's why we are saying the displacement, vertical displacement, can be expressed by a third order polynomial AX cubed, and so on and so forth. So once you realize, because we said it's assumed, the distribution function, we assume it, right? And it's a logical assumption, not just illogical, so on and so forth. All right, so now this constant, you need to get A1 and A4, and then using that, you need to do the derivation. I remember I made sketch also the shape function for the interpolating, the shape for the resulting interpolating functions, right? And this is a lot of marks, 8 marks. So I remember I made a tutorial on this. You can check it out. And of course, it's on the link. Also, on top of this video, I think on right or left, you can get that link so that you see how we derive this expression here. So this is what is repeated here. Yeah, how you went about getting the constant A by applying the boundary condition, right? All this derivation, we need to see these calculations. Shape function, interpolating function, and then at the end, this is where we sketch the N1, N2, N3, N4, right? And then later on, basic assumptions, material theories. Okay, I've given a lot of information here. You can summarize. Then you show the green one shows the FEM theory. Then I think the other will show, oh, the red. No, they shows the beam theory. The notation, because that's the one that we used towards the end to be able to come up with this expression. Okay. All right. You can get these. Of course, I always prefer students making their own notes, because as you do the hard calculation, you get acquainted with the procedure. And of course, you can come to this video and then scroll down. You are able to go to a certain part. But in case you're in a hurry and you want to refer to this tutorial, of course, to cater for my effort, not everything is free sometimes. So that's why I have hosted it in one of my, there's a website that we are hosting this material. So there are materials which are free, others you might need to cough up something small, but don't worry, you don't have to. It's there, you just come and copy. And copy here. Yeah, sure. All right. As I said, I wanted it to be that short and that simple, but I wanted to explain about this first part of the question, typical question. All right, make sure to click this link here, then it will take you to my YouTube channel, and then you can always subscribe and share with your friend. So especially if you have people who have never encountered in class, like you have friends in your university where I'm not teaching there, you are my ambassador there, so share this link and then tell them to subscribe, and we share knowledge to as many as possible. So if you refer to, let me refer you to the other one, which was for the supplementary. Let's see. So the thread is the same, compulsory 30 marks, short question, compare and contrast between finite element method and analytical method. That one you refer to lesson number 1. We have that table there. We compared. Outline the main procedure for finite element method. So the right procedure, each one will be a half. So here, comparing and contrast, you have to one point on this side and another point on this side, analytical and finite element. Otherwise, if you just state on one side, then you are not comparing or contrasting. So full marks will be awarded for 2 points line in line. So you expect 4 on this side, 4 on this side, you have 4 marks. Then procedures, 8 procedures, that will give you 4 marks, so half each. So what do you understand by time discretization? This is a breakdown of the overall structure to individual element or small m, right? Explain the principle of mechanics to finite element analysis, the principle of compatibility, static equilibrium, constitutive relation. Yeah, this one I explained them, and I believe I also gave them in a CAT. So in lesson number 1 and 2, you can be able to obtain that. But of course, compatibility is where you say the nodes remain together, so the information at the common node is the same. Static equilibrium, of course, remains a state of rest, or rest. The forces will be equal. Let me show you typically what I'm saying by this. Let's look at let's see model answers for. So yeah, like this is what I'm saying, compatibility, connected nodes of adjacent string, suppose they have the same displacement because they remain connected. Static equilibrium, the resultant forces at each node is equal to 0, so it remains in equilibrium. Constitutive relation, of course, is material, how the material responds to applied loads. So this is again the CAT, I think it was last year CAT. And these were the typical answers. Most of them I've given them in tutorial, in classwork, and so on and so forth. And this one is a repetition because, of course, we learn the same thing. Okay. All right. But I was concerned with part 1. All right. Now I was showing you the theory. I mean the supplementary, the theory part 1. So again, assume the actual displacement for a node or environment, blah, blah, blah. This is a repetition of what is in the other paper. So you can see sometimes we repeat because we are testing the understanding. I got motivated to share with you this because after maybe the typical order or format that you have been encountering might be slightly different from my case, and so it's good because we do not test students to fail at the university. We are training you, okay? At high schools and primary schools, that's where there is the sieving. We want to sieve the system itself, not me, but the system itself at primary school. They want to they go on eliminating. But once you have managed to go to tertiary institution, it's about training. But that does not mean that you don't need to study, you don't need to understand this concept. For me, my concern more, I wouldn't like to mark somebody getting an A and then maybe trying to copy. Actually, I loathe cheating in exams. So if you can refer to your colleague, for those people I'm teaching, kindly refer to your colleague. Now this for they are going to fail there if you are my student. And it would be unfortunate if I'm the one to stop you to go to failure if I get you cheating. Yeah, we just stop you and then I just delay you in doing the soup and you don't proceed. Because I believe at this time we are training engineers, or you're almost getting to the point of finalizing your year and then register become an engineer. Then you need to have that ethical thing. And I'm also training you to go to heaven, yeah? Right? For those who believe in so I'm helping you. And this reminds me, by the way, I've got a hobby. I like spreading the gospel, so you can click that link there. Some part of my hobby, I post sometimes videos here and there, motivational, encouragement, and so on and so forth. Because everything is not about engineering and mathematics and being so robotic. You have life outside there. All right. And then a simple one. This one is solved in the class. 2-bar assembly, 6.5 mark. Again, a repetition, driving the beam. So and in this time, this period now, what I did, you are not given the shape function. What you are given is that the UDL can be expressed as this. Fractional rigidity, the fourth derivative of the displacement. So now you should work backward, integrate, because we know the fourth derivative, you move upward, you get the issue of slope curvature movement is the second derivative. The shear force, I think, is it that or that, like that, until you get to the displacement, which is the integration to the fourth time. So you'll be having C1, C2, like so on and so forth. Okay. So either way, you can start, even without being given, you can start this point, you can start by assuming, and that's always fair. Okay, I want to stop here for part 1. This is a revision exam part 1. As you revisit your notes, look at this. If you get more time, we can have part 2 for this now detailed question here. But I remember like this one is already solved in a tutorial, so no need to cover this, and so on and so forth. This one was covered in the class. Oh, this was for the supplementaries for the last year. Usually the question I give for last year, then I use them for training this year. Then if I create other notes, I can just twist them a little bit, or I can create new questions. Then I use them for the next year for teaching. All right. Thank you for your patronage. Thank you for watching towards the end. If you find this video useful to you, it's very important and for this channel that you share this video, like this video. Never leave my video without liking, because they help the YouTube algorithm to notice the video and they recommend it to more people. We are trying to reach as wide audience as possible. I've put a lot of effort in this, so I would also be happy if it can touch many people out there, and as well as the channel growing. Again, subscribe, share the subscription link to your friends, to your colleague, and let's continue growing as a family. And if you have any question on any of the videos that I posted earlier on, leave the comment in the comment section for the benefits of the others. Thank you. God bless you. Until next time. Bye-bye.